Hello community, hello internet. Here we are now back to our second part on SBERT Cross-Encoder. So we are here in the sentence embedding field with the sentence transformer. We have a class that's called Cross-Encoders. I showed you in the part 1 of this video. You are now watching part 2 of this video. And I will show you an advanced example how to perform re-ranking with a cross-encoder for a semantic search. So at first, what we want to do, the first is we use a BI-Encoder, this means SBERT, to retrieve similar questions from a dataset. So we have a question and then we retrieve, I don't know, 100 or 1000 mostly similar questions. And then to retrieve the top 5 of those 1000 questions, we use then a cross-encoder. So we combine the BE-Encoder, that is fast but not really performant. We get the first 1000 results, and then to come from the first 1000 results to the top 5 results, we use a slow but very precise cross-encoder. Let's code it. From our sentence transformers, we need the sentence transformer, we need our utility function, and of course we need our class that I showed you last time of our cross-encoder. If you are still looking what is a cross-encoder, here we have the API. Within SBERT Sentence Transformer class, we have here the sentence transformer.cross-encoder cross-encoder. And what it does, it takes 2 sentences as an input and it predicts the score or the label for the sentence pairs, similar, not similar. It gives you back a numerical value in the interval of 0 to 1. We have no sentence embedding in a vector space. It does not work for individual sentences like a BI-Encoder. Cross-encoders return 1 numerical value for a sentence pair. Full stop. You can train those models with a specific fit function for cross-encoders. You can have a predict function for cross-encoders with all the different parameters. And what we're going to use now in a minute is you have a lot of specific evaluation functions. So they have their own class, of course, and they're in sentence transformers, cross-encoder evaluation functions. Heaven's sake. And it's all done for you. It's all programmed for you. You just have to type in this very short abbreviation of heaven's sake, and the code will perform for you. Isn't that great? And I will show you in a second which kind of evaluation function we will use for our example, but just as a short reminder. So here we go. We import CSV, we import pickle, we import sys, we import time. Yeah, this is it. So here we go. We use a BI-Encoder. This is a sentence transformer. This is SBERT that produces embeddings for our questions. So we have now a sentence embedding, a singular sentence embedding in a vector space, and a topological space is created by a BI-Encoder. And we then search for a similar question in this vector space by using a mathematical operation that is a cosine-similarity to identify the top 100 most similar question around this particular vector in the vector space, which was our original question. So we have our original question and the top 100 most similar questions that are close by in the embedded space, in the embedded vector space, and we do this with the cosine-similarity. For a model, for an SBERT model, we use here an old mini LM 6-layer version 2 model, a language model, and we have here the definition. We say model is sentence transformer and our old mini LM L6 version 2. Great. Now, to refine these results, we use a cross-encoder. Cross-encoder gets both inputs, the input question, this is our original question if you want, and the retrieved question, one of our 100 questions, and outputs a score of 0 to 1 in the interval 0 to 1, indicating the similarity of those 2 sentences in the sentence pair. Beautiful. So we run this 100 times and it's done. Now, how do we do this? How do we define our cross-encoder? Now, our cross-encoder should not be a tiny BERT L2 cross-encoder, but we need, at first, we need a STS benchmark dataset. And then we apply a big and advanced version of BERT, a Roberter, and we do not take the tiny versions on, but we take the base version. Or if you want, you take even the large version if you have the computer power available to you. And the dataset we want to use is simple, the quadruplicate question dataset. This is a predefined dataset. This is done. We just downloaded it. This is just if we already have it. If not, we downloaded it. This is it. And now comes the interesting part, because we say now the model encode our sentences, show us the progress bar, convert to a tensor, beautiful. Store the file on disk, yeah, beautiful. Open the disk, yes, yes, beautiful. And then we have this model. And with the model, we say, okay, we are ready to go. Now give me the first question. And the first question, as I showed you, is those first question that we will have a vector in the embedded vector space where we then have, with the cosine-similarity, given the training on a cross-encoder that was pre-trained on the SDS benchmark dataset. Now, with the quadruplicate questions dataset, we now have the option to input a question. And then what we do is very easy. We encode it, and then we have from the utility function, we do not use the cosine-similarity, but we use the little bit tuned version, the stronger cosine-similarity with semantic search from the utility function from SBERT. And the number of candidates is 100 as we defined it, or 500. What was the number? 500, number of candidates, 500, yes. And this is it. And this gets the hit for the first query. So we say the cosine-similarity search took seconds, yes, and the top 5 now from the cosine-similarity, we even say the top 5 of the cosine-similarity is this, this, and this. Ah yeah, we have to compare it, of course, that we see that there's an improvement. So the thing with the cosine-similarity in a vector space is done. But you see, we have not yet used any cross-encoder. This was just the normal thing that I told you here, the first 2 lines. We have SBERT, we have a BI-Encoder, we have a sentence transformer, and then we search for the similar question using the cosine-similarity, since the SBERT or the sentence transformer, the BI-Encoder, BI.encoder, gives us a vector embedding for each sentence. So this is it. And now comes the part when we say, okay, now we want to do the fine-tuning. Now we activate our cross-encoder. And here we go. Now we do the re-ranking with the cross-encoder. So now we say, hey, cross-encoder model, this is great. Please predict for the given sentence pairs. Now we have the 500 cosine-similarity sentence pairs. Please do the re-ranking, given that now we use a cross-encoder where we calculate the attention between each and every input token in our dataset. Now this takes longer, but it is more precise. So you say, okay, here cross-encoder score, then you sort the list by the cross-encoder score, and you say, hey, print the top 5 hits with the cross-encoder, the corpus, yeah, and we say, of course, this was the code originally by SBERT.net, by N. Reimers. He is the expert who provided this code sequence for us. I adjusted it a little bit, but if you wanna go along with me, here's the GitHub link for you to download this exactly example of a BE-Encoder with a cross-encoder, fine-tuning, a re-ranking with the cross-encoder as a Python file. I just adapted it a little bit. So, and then of course, I did a rerun to see if it's working before I started the video, but let's run it now. Since I am running on, what is my runtime? I think I have no GPU activated, heaven's sake. So I'm running on a CPU. Okay, takes a little bit longer. So we have the corpus loaded with 20,000 sentences, we have 20,000 embeddings, and then we have a question. And now I can start to ask my question, which will be embedded in a vector space, and then a cosine-similarity will take place, and we will get a ranking of the closest vectors in the vector space. And the question is Europe a continent? Continent. I should put my microphone somewhere else so that I can see my keyboard. So yeah, beautiful. So as you can see, we are operating here on SBERT. This means a BI-Encoder. So we are fast. 0.06 seconds. We're lightning fast for 20,000 sentences. And we get here the numerical ranking. You see, okay. The first is, why is that Antarctica is considered to be an ocean as well as a continent? And this is the top sentence in our 20,000 sentences. That is the most similar, calculated with a cosine similarity if we do the SBERT calculation. And we create for each sentence of our 20,000 sentences a vector in a topological vector space. And do the cosine similarity, and this is it. And then the second part is Greece part of the European Union. So because, of course, we have Europe here, there is also that it could be, I don't know, geopolitical question. Yeah? And then you see here we have the re-ranking with the cross-encoder. This is the fine-tuning now. And then we say, okay, you can see hardly a second, and then it takes us a minute. And now we have the fine-tuning with the cross-encoder. And of course, we only have 20,000 sentences to choose from our corpus. So it's, think about 10 million sentences, and you will get a real difference. But here you can see that here, the question that was part 2 is now the leading question. Which Europe is best for asylum seekers would happen. Want to join the EU, considered both an ocean as well as a continent. So you see here, question answer number 1 was most similar question here with the cosine similarity is now from the other top 5 cross-encoder is now the least similar. Okay. Now what else do we have? Jesus. Tell me about the, I don't know, Middle Ages. So not a question. Let's see what we get back. So, cosine similarity, lightning fast. Where, why, and how did feudalism start? Where was feudalism developed? Paleolithicum, Neolithicum, time periods. Jesus, the Bronze Age. Invention in the Neolithical Age. Yes, okay, man, it's not the Middle Ages, but okay, yeah. This is not the 12th century. The Neolithical Age is a little bit a factor 1000 in the past, but who cares? And now we wait a minute for, I'm running only CPU, for the calculation of the cross-encoder, the BERT model, where we calculate all the attention between all the different input tokens. So come on. This is it. Yeah, maybe I did show you a third question, and then I think this is already it for this little bit more complicated part. Oh, come on, it's not so complicated. Here we go. Cross-encoder took 65 seconds. Wow, this is something specific. What are the career choices for a middle-aged financial product sales professional in India? You see, this is almost the Middle Ages from a time period, yeah, of our planet. Now it's the middle-aged financial product sales professional. Heaven's sake. Yeah, if you have some semantic that is not absolutely clear, you get exactly this. How can you understand Middle East issues in a better way? Midlife crisis, Middle Ages, midlife crisis. Jesus. Ancient Israelite Egypt South. No. Enter a question. The weight of an electron. Let's have a look if in our 20,000 sentences we have an answer to the question. No. What does the scale measure? What is the different mass and weight? Yeah, that's a good question. Weighting scale. So weight, no. So clearly our, where is it? Our corpus with our 20,000 sentence against which we compare our single question. In this 20,000 sentences, there's nothing about an electron or quantum field theory or physics or particle physics. Whatever it is, you know what it is because it is, where is it? A quadruplicate question. My goodness, how boring. So, okay. Hold on. Oh, we're waiting for the cross-encoder to finish. Takes another 60 seconds. And of course, even a cross-encoder will not be able to find... Hey, yeah, there's an electron! Unbelievable! Remember the question, the weight of an electron? The mass of an electron. Yes, wow, a cross-encoder really did the job. Amazing! The mass of an electron. Stronger titanium or diamonds? Interesting, yes, has to do with the Jesus, what's it called in English? The electron, the wave function of the electron, depending on the äußere. I don't know, come on. And then the electron configuration of oxygen. Yes. Nice. So when we had with the cosine-similarity only, how is the mass of the electron calculated as the top 5 least similar question? We have now with a cross-encoder, the electron determined, electron calculated, electron configuration of oxygen. 3 really interesting questions that are in the body of our 20,000 questions. So this is really nice. This is great. So you can see, you can combine a BI-Encoder and a cross-encoder as a good pair, a good pairing of BERT models to have at first a very rough estimation. You take from the 20,000 sentences, you take just the first top 500 sentences. And then within the set of those 500 sentences, you apply a cross-encoder, a BERT model. You calculate all the different attention, the multi-heads, and then you have a set of answers, the top 5 answers, that are really, really better, now from my part of view, than the pure cosine similarity if you only apply SBERT. So if you apply at first SBERT and then you apply a simple BERT, you will get a similarity or question and answer or whatever sentence pair similarity that has a much better performance than just the SBERT model. Great question what we learned today. We are already almost 20 minutes into this video. I know it was a little bit more complex coding example. It uses the combination, a BI-Encoder, a sentence transformer, calculate the cosine similarity for similar questions, and on those results we get from SBERT, we apply a cross-encoder. On SBERT, we apply a BERT model. So this was it, and now we have the third video where finally, I don't believe it, we come to the main part. Because this was just the introduction part 2, and I needed this to show you now BERT domain augmentation. How we can use now cross-encoder of a particular domain where we have no labeled data to generate a labeled data set for SBERT, which is a BI-Encoder, so we can optimize the performance of SBERT through Cross-Encoder. And this will finally be the content of the third video. And if you are still with me, if you really still with me, I give you a peek preview what we will do in the next video. And I will show you how you can optimize the training from a different domain. Let's say you're trained, your BERT is trained or SBERT is trained on mathematics, and you want to have the SBERT model also trained on physics or medicine or I don't know, whatever you choose. We have a different target domain, and I will show you 5 steps. 4 steps are here. We start with a cross-encoder. And we have a golden labeled data set of a domain A. let's say this is mathematics or chemistry, whatever you like. Then we will fine-tune the cross-encoder with our golden data set. So we will get a cross-encoder, a golden cross-encoder, and I will show you a method, of course, by SBERT, invented by the beautiful people from SBERT.net, to create on a different domain, on a target domain, and this is now, I don't know, material science, let's say. Our new target domain is material science, where we have no labeled sentence pairs. So I don't know which two sentences are correlated or not correlated or neutral. Our golden cross-encoder will now do the labeling for us with this golden cross-encoder. So suddenly we will get more input data that are labeled, and then we have some supervised learning with a domain augmentation. Not only that we get more amount of data, but we have also that from a, domain A and a domain B, we have now a learning that includes domain A and domain B. So a knowledge transfer, if you want. And then with this new labeled data, finally we can start up our specific BI-Encoder, our SBERT model, and we can do a supervised learning on the new mega labeled target domain. And this helps us to increase or receive a much better performance by SBERT. And we have not only the first domain knowledge included, but also the target domain included. And if you compare this method to a pure SBERT method, I will show you that there's some nice advantages, some nice performance gains you can get if you do this domain augmentation for SBERT. And in detail, the code will be in the next video and you're waiting for it. And of course, I tell you, see you in the next video.